Combustion analysis is sometimes a process which is used in order to determine the empirical formula of hydrocarbons. Now, what do I mean by a hydrocarbon? I mean a compound that has carbon and hydrogen in it. It sometimes has oxygen, but it's not necessary. It's built on carbons and hydrogens, sometimes oxygens. Now, what we do with this hydrocarbon is we combust it. Remember, in order to burn a hydrocarbon, what we need is oxygen. And when we burn a hydrocarbon with excess oxygen, what we always get as our products, carbon dioxide and water. So we take some grams, some initial amount of our hydrocarbon. Here it was 0.165 written down. We add oxygen, and then we get masses of carbon dioxide and water. Notice the masses afterwards are more than the initial mass that I began with. Why? Because I added oxygen to it. When I add that extra element, I get more mass. All right, we're going to go ahead and use this data in order to determine the empirical formula of this original compound. If you want an empirical formula, that's really just the lowest mole ratio. So what we're really going to need to do is find the moles of our carbon. We're going to need the moles of our hydrogen. And finally, we're going to need those moles of oxygen. If we can find the moles of each of those elements, percent to mass, mass to moles, we divide by the smallest, we got ourselves a ratio. So how do we do that? Well, the key is to start with the products. Looking at the carbon dioxide is going to give us information about the carbon. There's only one place that the carbon in this hydrocarbon went to. It went into carbon dioxide. So we can use the carbon dioxide number to give us information about moles of carbon. Let's start there. I'm going to go ahead and start off with my 0.403 grams of CO2. I want to take that all the way over to moles of carbon. So the first thing I need to do is get rid of grams and go to moles. 1 mole of CO2 in this case, if we add up 1 carbon and 2 oxygens, we get a molar mass of 44.01 grams. Grams go away. Now I'm at moles of carbon dioxide. I don't want moles of carbon dioxide. What I want are moles of plain old carbon. So we need to go an extra step. We need to get rid of moles of CO2. I'm going to put that diagonally on the bottom, and I'd like to go to moles of plain old carbon. Now looking at our formula, for every 1 carbon dioxide, there's 1 carbon. This is just a 1-to-1 mole ratio. So we're going to get exactly the same number. If you take 0.403 divided by your 44.01, I get 0.00916 moles of C. Now that is such an important number that I'm going to try to stay organized. It's going to be a long problem. So I'm going to write that information up here. 0.00916 moles. I'm going to need it. Now, we also need to go ahead and get the moles of hydrogen. The information that's going to help us with that one is water. The hydrogen in our original compound only went 1 place, and that's into the water. So we can take the number they gave us for water and backtrack that over to moles of hydrogen. Let's do that now. So we're going to take our 0.166 grams of H2O. What can I get to from grams? Moles. So we're going to get rid of grams on the bottom. We're going to go to moles of water on the top. 1 mole of water is 18.02 grams. Grams go away. Now, that's going to give us moles of water. Lots of students stop there, and it's the biggest mistake students will make in these problems. We don't want moles of water. We want moles of hydrogen. So we need to go one more step. we're going to get rid of moles of water, putting them on the diagonal, moles H2O. We'd like to go to moles of plain old hydrogen. And if we look at water, there are 2 hydrogens for every 1 water molecule. So this is a 2-to-1 ratio. Moles cancel out. Now, if you go ahead and do the math on that, I get a value of moles of 0.0184 moles of H. Okay, again, super important number. We're going to need it. Let's stay organized. 0.0184 moles of H. All right, now what about the oxygen? When we look at the oxygen, we can't just use the carbon dioxide number and backtrack that to the oxygen. Why? The oxygen here went multiple places, not just to the carbon dioxide. The oxygen here went into the carbon dioxide and the water, and extra oxygen got added to those 2 numbers. So what are we going to do? What is the key here? How can we go about finding the amount of oxygen? Because we need moles of O. The key or the trick to this is using the total mass. So if we know that the total mass is 0.165, that total mass is composed of carbon. Hey, we have information about carbon. That mass is composed of hydrogen. We have information about hydrogen and oxygen. We can get the amount of oxygen if we take the total here and we subtract the grams from carbon and we subtract the grams from hydrogen. What's going to be left over are the grams of oxygen in our compound, and we can use that value to get the moles of oxygen. So we need to go ahead and go further in our problem-solving process. We don't have grams of carbon currently, but what we do have are moles of carbon. We can change those moles into grams using the molar mass. So we got to go a step further. Let's get rid of moles of carbon. 1 mole of carbon is this 12.01 grams. If we do that, we're going to go ahead and get a number of grams for carbon of 0.110 grams. Okay, that I'm going to go ahead and write over here. 0.110. And I'm happy because it's less than my beginning value. If it was more than my total, I know I'd have some issues. Now we're going to do the same thing with our hydrogen. We have moles of hydrogen. Let's change those into grams. So hydrogen has a beautiful molar mass. 1 mole of hydrogen is basically 1 gram. We can use 1.008 grams, 1.0079. And if we do that, the number of grams for the hydrogen turns out to be about the same, 0.0186 grams. Now again, I'm going to subtract that from my total, 0.0186. Now, if you go ahead, take the grams of carbon and the grams of hydrogen away from your initial total mass, we get the grams of oxygen. When I did that calculation, I got 0.0364 grams. Now, 0.0364 grams, that doesn't go here, that's not moles, but it's gonna help us get the moles. So I'm gonna go ahead and write that down over here. We have 0.0364 grams of oxygen. I'm gonna change that into moles of oxygen. 1 mole of O has a molar mass of 16.00 grams. If you divide your grams by the molar mass, I get moles to be 0.00228 moles of O. And again, remember, that's a super important number. We're trying to stay organized in all of this chaos. So I'm going to write that right here, 0.00228 moles of O. Percent to mass, okay, we had some masses we got to play with. Mass to moles, we've got our moles. The next step to get a ratio, divide by your smallest. So the smallest out of all of these ones is your 0.00228. I'm going to divide each of my numbers by 0.00228. 0.00228, and this one 0.00228. Now, if we do that, your numbers turn out to be, the carbon comes out very, very close to 4, close enough we can call it a whole number. The hydrogen turns out to be 8. This divided by itself turns out to be 1. So percent to mass, mass to moles, divide by small, make sure they're whole. They're whole numbers. We can write our empirical formula. So the empirical formula at this point, we have 4 carbons. I'm going to write that right here, C4. We have 8 hydrogens, H8, and then we have 1 oxygen atom, O, and we leave out the subscriptum 1. So there is our empirical formula using combustion analysis. I hope that helps. Stay organized. Take care.